Okay, so good morning everyone. Again, welcome to the FisMat2015 conference. My name is Dario Pisignano. I'm from the University of Salento and the Nanoscience Institute of CNR. And I'm really honored to introduce you the first plenary speaker of the conference, who is Professor John Rogers. Just a few words about Professor Rogers. He obtained his BA and BS in degrees in chemistry and physics at the University of Texas. Then he was at MIT, where he obtained his PhD degree in physical chemistry, and he moves then to the Bell Labs in the condensed matter physics research department. He was there until 2002, and he was also the director of this department. He currently has a position at the University of Illinois at Urbana, Champaign, and a primary appointment at the Department of Material Science, and is also currently the director of the site's Materials Research Lab. And as you know, he's a world leader in the fields of patterning and lithographies on unconventional materials and for unconventional electronic and photonics devices. And in particular, as you will see in the talk, this is in the spirit of biointegration and biomimetic materials. And he published so far more than 450 papers, and he's the inventor of more than 80 patents and patents applications. And I would also remind that from 2015 he is also a member of the National Academy of Sciences. So again, Professor Rogers, thank you very much for being here, and please, the stage is yours.
Grazie and buongiorno. Those are my two Italian words that I know. So I'll give you a talk in English and maybe more appropriately American about some of the work that we've been doing at Illinois in my group there. My own background is in material science and engineering, condensed matter physics, but this talk will be not only about the science, but about some envisioned applications that we think would follow from successful efforts in scientific research. And so to that end, I'll begin with kind of motivation of what we're trying to do, a little bit of perspective around what we're attempting to accomplish with semiconductor nanomaterials and electronics. It's a little bit different than standard electronics in the sense that we're interested in biointerfaces and in particular bioresorbable forms of technologies of this type. It's really in two parts. The first part will be focused on this sort of bioresorbable electronics. More generally, we refer to it as transient. It's physically transient in the sense that it disappears over time. For specific applications in biomedicine where we think that kind of technology could be useful. And then in the second half of the talk, I'll describe some approaches to build not only these kinds of electronic devices, but other ones as well, in 3D architectures that may allow for higher levels of functional integration with biological systems. So let me begin by just reminding you something that you already know, which is semiconductor technologies are ubiquitous parts of our daily lives. One of the most successful technologies, I think, of all times. In the last half century, we've gone from computing systems that would take entire rooms to devices that we put in our pockets that offer, a million times higher levels of functionality than was previously possible. It's really a technology that's all about miniaturization. That's what's driving these advancements. And so from a technology standpoint, you could rightly speculate that the future of this technology will rely on more of the same. Continuing this size miniaturization, making the individual switching elements in these technologies, the transistors, faster and faster, and at the same time developing advanced manufacturing technologies that allow you to build them at lower and lower cost per switching element. And that's kind of a technology perspective on electronics. It also sets a roadmap for scientific research as well. Because in order to enable that kind of future, there will need to be fundamental advances in our basic understanding of how charge transports and interfaces in nanoscale structures and so on. So that's from a science and engineering standpoint. What may be just as interesting is to think about the societal implications of this technology, where in the early days, computing systems were really designed for narrow purposes in industrial and scientific research. to the state where it's really permeating every aspect of our daily lives today, where it plays a role not so much in computation, but in communication and entertainment and productivity enhancement. And so one could wonder, what will the future hold from this kind of applications or societal perspective? And I think a lot of folks have a lot of different ideas, and there's a lot of promise in that direction. What we believe is the future will involve one in which these devices become intimately integrated with the human body for specific purposes and improvements in human health outcomes, where one needs to think not only about making the computational infrastructure more and more powerful, but in designing the devices, the physical characteristics of the devices to look more like biology. So if you think about electronic circuits as they exist today, they're all built on the rigid planar surfaces of semiconductor wafers, and that's fine if you want to build devices like a smartphone or a laptop, you put it in your pocket or in your backpack. But if you wanted to take this kind of technology, man's most sophisticated electronic system, and bring it to bear on biology's most sophisticated form of electronics to understand how it operates and to develop new kinds of interventional procedures to deal with brain disease, you would have to think about the mismatch between the mechanics and the geometries of these kinds of systems and the human body, the brain, in that context. And solving that challenge would not only have implications on how we think about neuroscience and neurosurgery, but also how you could potentially treat heart disease, develop classes of electronics that could wrap the outside surface of the heart, which itself is an electromechanical system. Or if you want to do continuous health and wellness monitoring, the skin itself is a window into all kinds of underlying physiological processes that could be monitored accurately if you could take this kind of technology and sort of melt it into the surface of the skin. And so in those kinds of technology, you have to worry about not only speed and cost, but actually functional form and mechanics and shape and geometry. And if you think about that as a challenge, you may reach the conclusion that silicon itself is no longer going to be a sensible foundational material for those kinds of devices, because one thinks of it in the form of a silicon wafer, which is highly mismatched from the kinds of surfaces and textures and mechanical properties that you see in biology. And so you might conclude that it would be worth looking into semiconductor polymers, for instance, or carbon nanotubes, or graphene, other kinds of materials. I think there is merit in going down that path. Where we've had the greatest success is to just figure out how you might be able to deploy silicon in different ways, non-wafer formats. And this is a slide that just highlights some really simple aspects of fundamental mechanics of silicon as you make it super thin. So if you think about silicon not as a wafer, but as a nanoscale membrane, so very thin sheets of device-grade monocrystalline silicon, but with thicknesses maybe in the 10 to 50 nanometer range. A couple of things happen when you make a material that thin. The first is fairly simple, which is the bending stiffness decreases with the cube of the thickness. So when you go from a wafer thickness, maybe a millimeter in total thickness, to something in this nanomembrane regime, because of that cubic scaling and thickness, the bending stiffness decreases by 15 orders of magnitude, from about 10 newton meters to about 10 femtonewton meters. And that's just elementary Newtonian classical mechanics, but anytime you take a physical parameter and you reduce it by 15 orders of magnitude, that has a qualitative way a qualitative impact on the way in which you think about that material. So silicon in nanomembrane form is no longer necessarily rigid, it's really floppy. And furthermore, the peak strains associated with bending a sheet of material to a radius of curvature are decreased linearly with thickness. So not only does it become floppy in the sense of the very low bending stiffness, but it becomes very bendable in the sense of being able to reach very tiny radii of curvature, where the peak tensile strains that will initiate fracture in a brittle material like silicon is about 1%. So that's a way of thinking about silicon that's a little bit different. You have to alter the way you think about how you construct electronics out of silicon, because this is no longer a sensible choice for a substrate, as a silicon wafer would be. So you have to think about it as a building block material that you would heterogeneously integrate on a substrate of interest, like a piece of plastic or a piece of rubber. And in that case, you're talking about extreme levels of heterogeneous integration, where you might want to bond silicon to silicone rubber. So those are dramatically different types of materials. And ordinarily that would be a rather daunting challenge just in terms of interface adhesion management. But here the thickness scaling comes to your rescue again, because the energy release rate parameter G scales down linearly with thickness. So although it's practically very difficult to glue a silicon chip to a piece of rubber, a silicon nanomembrane will adhere relatively easy to a material surface like that because the energy release rate is many orders of magnitude lower. Again, it's linear scaling in this case, but many orders of magnitude reduction from a wafer scale thickness to something in this nanomembrane regime. So here's an example of that. A very thin piece of silicon bonded to a ridge that we've micro-machined into a piece of plastic. It's just van der Waals forces that are holding this thing in this cantilever geometry, and it's partly due to that, the linear downscaling of this energy release rate parameter G, which defines the propensity of a crack to open up between two dissimilar materials. So those are some pretty simple ideas. You know, the next question would be, if you want to use a material like this, how do you make it in the first place? You can't take a silicon boule and slice it into sheets that are that thin, you know, analogous to the way you would form a wafer. But there are chemical etching techniques, anisotropic etching approaches, that allow you to take a silicon wafer, and I won't go through the details, you just note that you can do this in fact, and shave from the surface of the wafer extremely thin membranes or ribbons or wires or platelets or other kinds of geometries in device grade silicon. So this is silicon nanomembranes being peeled up from a silicon wafer, and you see the kind of mechanics that I mentioned to you before. So that gets you into a regime of devices that could conceivably be flexible. You could take these ribbons and you put them on a sheet of plastic, and that would be good. But if you want to integrate with the brain or the heart or the skin, any kind of biological system, simple mechanical flexibility is not enough. Because if you have a sheet of plastic, you can wrap a cylinder or a cone, but you can't wrap a sphere, much less a brain surface. So what you need is something that not only bends but stretches as well, more like a rubber band. So it offers linear elastic response to large strain deformation, not just bending deformations. And so there you can't you know, accomplish that kind of mechanics by making the silicon super thin. You have to do something else. So sort of idea number two is you can take these thin pieces of silicon and you can bond them to underlying rubber substrates that define the low modulus, high elongation mechanics. But do that in a structured geometry, in this case sort of a wavy shape, to create sort of a hard, soft composite material that offers the mechanics that's very similar to that of an accordion bell. So now you have something that can stretch, but embeds a high-quality, brittle semiconductor material for the active components of the devices. So those are some of the ideas. If you put those together and you add on top of those concepts, you know, engineering elaborations, it turns out that you can begin to build the kinds of systems that I described to you previously. So you can now make high-quality electronics that can conform to the contours of the brain, including the sulci and the gyral surfaces, for mapping out electrical activity on the surface of the brain to yield new insights into the function of the brain. And you know, around brain disorders such as epilepsy. We've done a lot of work in that area. Same ideas apply to the surface of the heart as well. Here's an example of a multifunctional electronic system that wraps the entire epicardium. And so the goal here is to map out electrophysiological behavior associated with arrhythmias, for example, and to stimulate the heart in a much more complex, highly functional way than is possible with a conventional point contact electrode and pacemakers that exist today. And so if you think about a device like this as an advanced diagnostic and pacemaking tool, you might want to construct the electronics to last forever, or let's say to last the life of the patient. That might be an ideal scenario. And in principle, you could envision doing that because transistors obviously are solid-state devices. They were invented in the early days because they could be engineered with essentially infinite reliability, unlike vacuum tubes that were being used in the early days for communication infrastructure. And so in principle, you can imagine doing that. There are some practical challenges, particularly in the sense of biofluid barriers. You need to isolate the electronics from the surrounding biofluids to avoid unwanted you know, electrical leakage to the surrounding tissue. But those are solvable problems, and one can work on that. What we found, though, is in building systems like this, it turns out that there are application opportunities that don't demand the devices to last forever, again, the life of the patient, but instead have only a transient function. They are only needed for a particular time scale associated with, for example, a wound healing process. And after that process has terminated, you might not need the devices anymore if they were doing a diagnostic or therapeutic function in the context of that wound healing. And in fact, you might not want the devices to last beyond that time frame because they would represent what would otherwise be unnecessary device load on the patient and associated health risk. So that brings me to a different concept not simply bio-integrated devices, but devices that are designed to be bioresorbable, in the sense that at a molecular scale, you construct the electronics out of collections of materials that will dissolve at controlled rates in biofluids and terminate in biocompatible end products. So they simply disappear without a trace, but in an engineered, controlled way over time. And that kind of technology, you think about it as bioresorbable. You can imagine similar kinds of devices that might resorb in the environment to open up new kinds of opportunities. And these ideas have not only relevance in healthcare or environmental monitoring, but other areas potentially as well. If you think about the initial motivation of the development of the transistor at Bell Labs in 1947, it was designed to offer a very high reliable alternative to vacuum tubes. And really every engineering effort since then has been to design the materials, the device constructs for infinite lifetime. And essentially that goal has been accomplished. So we think about the guts of your cell phone. Those integrated circuits will last 50 to 100 years, no problem. And that may make sense in the case of information infrastructure, communication infrastructure, but there are a few people these days who want to keep their cell phone more than maybe a couple of years. So why are we designing the guts of these devices to last for 50? People are wanting to throw them away after a couple. So that creates another context in which this kind of technology could be of interest. So the broader definition is this. Transient electronics is kind of the way we think about this, where it embodies any kind of electronic system that can fully or partly dissolve or resorb or otherwise physically disappear at some programmed rate or at a specific triggered time is the way one could think about it. And the potential applications are as follows. So I mentioned all three of these. Let me just recap. Devices in consumer electronics, where you would want to eliminate or reduce toxic electronic waste streams because these kinds of electronic devices are being discarded at an ever-increasing rate these days. So that might be interesting as an application. Implantable therapeutics or diagnostics go inside of the body, live as long as they need to, but then after their function is no longer required, they simply disappear and dissolve away in the body. You can imagine devices that distribute out into the environment where they perform a monitoring function that also has only a relevant finite time frame. So remediation of chemical spill, for example. Once that's completed, you might not need the monitors anymore. It'd be nice if they could simply resorb into the environment. Those are three that we're interested in. I'll tell you some more about specific biomedical devices that address clinical unmet needs in a little while. This is the area that we're most interested in. This is the area where we receive all of our funding. It turns out that there are a lot of military systems, covert devices that you would not want an adversary to recover that benefit from these kinds of concepts as well. And this is another area that we're working in. I can't tell you the details about those systems, but just mention that they exist. So from a material science or condensed matter physics standpoint, how do you go about building devices that offer high performance, reliable functionality, but whose end of life cycle involves complete dissolution and disappearance at a molecular scale? And if you think about the different components of an electronic circuit, probably the semiconductor material is the most challenging one, which is generally the case. And so you can begin to think about what are the classes of materials one might contemplate for transient electronics. And you might want to separate those in terms of whether they're inorganic or organic. And if you think about bioresorbable electronics or environmentally resorbable systems, your attention may be drawn naturally to polymers because there's a lot of chemical versatility in the composition of those polymers. And so you can imagine engineering them to have simultaneous acceptable charge transport characteristics in the sense of their semiconducting properties, but out of materials that are intrinsically biodegradable. And that's certainly one way to go. There are a number of groups who are working along those lines, trying to do polymer synthesis to build semiconductors that are relevant for transient electronics. But that development of polymer semiconductors has a long history, probably 20, 30 years. And even the very best polymers offer field effect mobilities, which is what's indicated here in sort of this log scale, that are comparable to amorphous silicon. So far short of what you can achieve with monocrystalline silicon and what you might need to do, high performance electronics, microprocessors and radios, for example. And so polymers may not, be a realistic solution here. Other kinds of organics, you might think about carbon nanotubes. I think the toxicity there represents a large question mark. Various 2D materials may be interesting as well. At the same time, all of these relatively new materials may represent important candidates, but you'd have to recognize that if you could figure out how to use silicon for transient electronics, that's probably what you'd want to do, because there's already a very deep base of scientific and engineering knowledge around silicon due to a half-century of global R&D around that kind of material for integrated circuits, and on top of that, a very sophisticated manufacturing structure for developing highly functional devices at very reasonable cost. So what about silicon? You typically think of silicon in this wafer format. I was referring to that format for silicon in terms of the mechanical properties and the geometrical layouts, but you can think about silicon in this way in the context of transient electronics as well. And I think most folks had previously thought about silicon as a rock in the sense of its chemical properties. I mean, if you take a silicon wafer and you drop it in a bucket of water, nothing is going to happen, nothing very dramatic. And that is true to some extent, but it turns out it's only true to 0th order. And in fact, if you take these nanoscale membranes of silicon and you're patient and you insert them in water at physiological pH, which is very slightly basic, and physiological temperature, 37 degrees C, you can actually watch it disappear. So here's an atomic micrograph with expanded Z-scale, so about 100 nanometer thick platelet of silicon, 3 microns on the side, immersed in an aqueous solution, buffered at pH of 7.4. And you just take AFM images of that piece of silicon as a function of time. You'll see that it completely disappears on a time scale of about 2 weeks. And that was surprising to us. I think it was surprising to a lot of people. You can actually map out the kinetics, measure the height of that nanomembrane of silicon as a function of time. You can see it sort of linearly dissolves with a linear reaction kinetics over time. So this is thickness of about 90, 70, and 40 nanometers, roughly the same slope in all cases, just a few nanometers per day. It's a very, very slow rate you'd never notice at a wafer scale, but if you're talking about a semiconductor nanomaterial construct for the silicon, this dissolution rate, although very, very slow, has profound consequence in the sense that it can completely consume the silicon on a reasonable time scale from the standpoint of biology, so a couple of weeks. So we speculated the reaction chemistry is this: is silicon reacts with water to form silicic acid, SiOH4, and a little bit of hydrogen. And if this is what's going on, that's good news, because silicic acid is naturally occurring in biofluids, groundwater, ocean water. It's non-toxic. And in fact, you generate such a tiny amount of this material anyway, because you're starting with such a tiny mass of silicon. Really doesn't matter. The naturally occurring concentration of silicic acid overwhelms the amount of material that you generate from this kind of chemistry. So what's happening is really a surface erosion type of reaction, very little diffusion of water into the silicon, and as a result you end up with this kind of linear reaction kinetics. So we can sort of confirm that speculation in terms of the chemistry by doing MD simulations and DFT calculations. This is an example of the reaction at a nanocrystal of silicon in water at neutral pH. And this movie will show the dissolution of that silicon atom off of this nanocrystal associated with reaction of free hydroxyl groups with the silicon, and it will eventually evolve as silicic acid. And you can imagine if you allow this thing to propagate sufficiently long, that entire piece of silicon will be dissolved with that as the reaction product. So just to sort of emphasize that point, silicon for transient electronics would be in this super thin nanomembrane geometry, maybe 35 nanometers. Thick enough, by the way, to support all kinds of advanced electronic function, as evidenced from the fact that SOI, silicon on insulator substrates, are commercially used, where the top device silicon can have thicknesses in this range. You take that silicon, you immerse it in aqueous solution, buffered at physiological pH and temperature. It dissolves completely in about 10 days, so 3 to 4 nanometers per day. And you only need about half a milliliter of water to dissolve a silicon membrane with that thickness and a 1 centimeter square area, maybe comparable to what you would expect for a microprocessor, before you begin to worry about solubility limits in the silicic acid. If you think about silicon for conventional electronics, you're talking about a bulk wafer, 700 microns in thickness. If you extrapolate this rate, you'd have to wait 600 years for it to dissolve, and you'd need about 8 liters of water to dissolve a 1 centimeter square chip at that thickness to avoid solubility limits. So this kind of thickness is relevant for transient electronics of the type that you might want to put in your body. This kind of silicon electronics is not relevant. So that's some of the chemistry. You can study this in a systematic way. So you can look at dissolution of silicon as a function of pH. If you think hydroxyl groups in the surrounding water are important, then you should see dramatic rate change as you change the concentration of OH groups. So we run from pH of 6 to pH of 14. You can see the rates increase very dramatically with increasing pH, as you might expect. And if you look at the scaling with concentration of hydroxyl groups, you find that it obeys a scaling law, the kinetics, that's comparable to what people previously understood for silicon micromachining, which happens in this kind of pH range. So that same chemistry persists all the way down to neutral pH, even slightly acidic levels, so that the silicon is dissolving. It's just dissolving at a much lower rate. And it has expected Arrhenius temperature dependence. It turns out, however, that things are a little bit more complicated. This is essentially corrosion chemistry, and as a result, you might expect that the concentration and the ionic species in the solution would be important as well. Turns out that that is, in fact, the case, and we made a detailed systematic study. I'll just show you some typical solutions that you might be interested in the case of transient electronics as part of our effort to just build a database to understand how the dissolution rate varies with different types of solutions. So you can take tap water, deionized water, spring water. Again, height is a function of time. The rates are varying a little bit here, fraction of a nanometer per day. If you take silicon, you immerse it in milk. It's a little bit acidic at room temperature, but there's a lot of other components in milk that evidently have the effect of accelerating the dissolution rate way beyond levels that you expect at a pH of 6.4. And in fact, a 70 nanometer thick nanomembrane of silicon is completely gone in 3 days of immersion in milk. Look at bovine serum, different kinds of biofluids, even faster. So at room temperature, less than 2 days, 70 nanometers of silicon is gone. At physiological temperature, less than 1 day, it will completely disappear. And then just for fun, we took soda, Coca-Cola. You can immerse silicon in Coke. So it's very acidic pH because of carbonic acid. But even there, it's dissolving at a finite rate, nanometer per day or so, because there's a lot of other components of Coke that are playing a role in that dissolution chemistry. So that's a little bit about the material science of silicon for transient electronics. How do you build functional devices? And it turns out that silicon is a great choice for reasons I just described for the semiconductor. There are lots of other choices, it turns out, for metals in the dielectric. So magnesium is a good one. People have used magnesium as intravascular stents in the past as a mechanical component, bioresorbable in the body. You can use it in thin film form to develop electrodes and interconnect traces for electronics that use silicon nanomembranes for the active material. Silicon dioxide, it's water soluble as well. Same reaction product, silicic acid, same chemistry as with silicon. Magnesium oxide is another option. For substrates, we like to use polymers, and biopolymers are attractive choice. Silk, in particular, silk fibrin can be extracted from silkworm cocoons. It's already FDA approved for resorbable sutures, so we figure that's a good choice. You can make a substrate out of that. It's basically like a piece of plastic. And then you can build all the other components on top of it. And this is an example of a Cole-Pitts oscillator. It's a radio frequency oscillator that involves a number of different building blocks that you might think about for electronics. So we used it as a test vehicle. MOSFET over here, transistor, RF diode, resistor, inductor, and capacitor. You put the whole thing together on a piece of silk, and you make a piece of electronics that has the kind of operational characteristics that you might expect, but whose key defining characteristic is an ability to completely dissolve in water. So you immerse this in water, everything dissolves away. The silk in this case dissolves in a few seconds because it's largely amorphous. We'll come back to that in a second. The magnesium at these thicknesses dissolves in a few hours, and as I mentioned before, the silicon dissolves in a couple of weeks. So this is a movie of one of these Cole-Pitts oscillators, completely water-soluble, high-performance electronics, and this is a video we developed for DoD funding agencies. So you can imagine you drop this in the grass, you just have to wait until it rains, and it will dissolve away. Your adversary won't be able to recover it. So Silicon is a spectacularly good choice of semiconductor because you can tap in immediately to the very deep and broad library of silicon devices that have been developed over the last 40, 50 years. So you can obviously do transistors where mobilities are comparable to what you would see in a similarly designed device on a silicon wafer. So a factor of 1,000 times better than anything that's out there in terms of polymer-based semiconductors, high on-off ratios. You can build different kinds of logic gates. So this is an inverter circuit. It's just a simple building block of a digital integrated circuit. You can build all kinds of sensors as well. I'll come back to this in a little bit. Silicon is piezo-resistant. So it responds to strain in changes in resistance. And so you can make strain gauges, and the orientation of the silicon ribbons in this particular layout defines the directional sensitivity to strain. So you can bend this all on two axes and measure changes in resistance and infer from those changes in strain. You can also make photodetectors. Silicon pin diodes are widely used in industry. You can also use blocking diodes to develop a passive matrix readout for an array of silicon photodiodes. And in fact, you can make a simple imager. This was a challenge from the DARPA program managers funding our work. So it's an 8x8 array of passively matrix address silicon photodiodes. So each one of these nodes consists of a silicon pin photodetector, a blocking diode to allow passive matrix readout, and then the appropriate electrodes and interconnect structures to make cameras. So you can take pictures with this device, but then it also has the ability to completely dissolve in water. So with that, I'm just going to summarize, a number of other materials that we looked at. We've done a ton of work in this area in the last 3 years. So it turns out there's a pretty decent choice of semiconductors. Zinc oxide is interesting because it's direct band gap, it's piezoelectric, and it's also water soluble and biocompatible. It dissolves to zinc hydroxide. So thin film electronics, you do it IGZO. Various forms of silicon, also water soluble, as you might expect, polycrystalline, amorphous, nanoporous silicon. Germanium is the first material back in Bell Labs that was used to make transistors. It's water soluble, well known solubility there. Silicon, germanium, high speed radio devices. Silicon single wall nanotubes, you could imagine that as sort of a disintegration type of mode of transients. Various kinds of dielectrics. Silicon nitride, also water soluble. People don't realize that. It dissolves to ammonia and silicic acid. So magnesium oxide, spin-on glasses. A number of different interconnect metals. I talked about magnesium, but zinc, tungsten, molybdenum, and iron. Also water soluble and biocompatible. You can make pastes of them. So you can make printable antennas, for example. And then a bunch of different kinds of substrates. Silk, PLGA, PLA, PCL, POC, collagen, polyanhydride. And also use foils of these metals as substrates as well. So if you want to use these things in the body or in different kinds of biology application, you have to worry about toxicity. So you can do those kinds of studies at an animal level or at a cell level. I'll show you a little bit about what we've done at the cell level. So you can take arrays of silicon nanomembranes, you can create cell culture on top, and you can incubate and proliferate cells right on top and watch what happens. So in this case, we're using a silicon on insulator wire wafer. We just have to pattern the silicon, and interference effects allow you to actually see these silicon nanomembranes directly, even though their thickness is only 100 nanometers. So that's what you're seeing, an array of these membranes. There's a top-down reflection mode, optical micrograph. You can see the cells as well. And you can watch what happens as a function of time. By day 4, silicon's completely gone. Cells don't seem to mind. They simply grow and proliferate as if the silicon weren't there. And you can measure by AFM, so not only watch optically the silicon dissolve, but you can, as before, watch the thickness decrease. And in this particular growth nutrient solution, the silicon is dissolving at a rate of about 80 nanometers over three days or so. You can also do animal studies. We've done about 150 animals. In this case, we take functional transient electronic platforms like that Cole-Pitts oscillator, and we simply implant it in mice models in this case. Subdermally, different regions of the body, and you allow it to remain there for 3, 4, 5 weeks, and then you come back in and you can do histology. And you look for inflammation or immune response. We haven't seen anything, and that might not be an unexpected result because we're choosing materials whose reaction products we know from previous work is biocompatible. So magnesium, silicon, silk, and SiO2. So there's reason to believe that these things will be suitable for use in humans as well. We're not there yet, but that's kind of where we are at this point. Now let me tell you one specific example of about a half a dozen of different types of biomedical devices that we're working on, just to give you a sense of the utility of this kind of technology, potential utility in healthcare, real clinical care. So we work with experts in traumatic brain injury at Washington University's medical school in St. Louis, about 3 hours south from us. And it turns out that if you suffer a traumatic injury to the brain, you go to an operating room or an emergency room, the doctors, like the ones that we work with, one of the first things that they'll do is they'll insert into the intracranial space a pressure and temperature sensor, because those two parameters are critically important. If they fall outside of a finite range, it could have profound negative health consequences for the individual. And the way that those sensors are done right now is they're non-degradable. They're basically fiber-type devices that insert into the intracranial space, but you don't need them forever. You only need them until the patient has recovered, and then you have to pull them out. And currently that requires a secondary surgery. It involves wired operations, so while the sensors are in, it restricts the movement and causes considerable discomfort in the patients. And it requires an external interface, so you can't seal the surgical site. And as a result, there's a risk for infection and hemorrhage during the device use, and in addition to that, risk associated with the secondary surgery. So the vision would be, throw all this stuff out, replace it with bioresorbable pressure and temperature sensors that could insert into the intracranial space and just stay there to eliminate the need for that secondary surgery and the extraction process. Have them configured for wireless operation, so you eliminate the constraint, the wired interface, and you also develop a kind of implementation that doesn't require suturing, and so it removes some additional risk. So how do you do this? We've been working on it for the last year and a half, 2 years or so, and it turns out that you can kind of put all the pieces together and make it work. The pressure sensor is the most difficult part, it turned out. Let me show you exactly how that works. So we have a nanoporous piece of silicon. We just use that as the substrate. It has good dimensional stability and good mechanics. That's the reason why we like it. But the total amount of silicon is very low. It's about 90% porous. But we can machine on top of that a trench, and we can cap the trench with PLGA, therefore by creating a drum head, essentially a suspended membrane, that will deflect when the pressure of surrounding fluids changes. And we can measure that deflection by exploiting these piezoresistive strain gauges I was talking to you about before. So we take these silicon nanomembranes, in this case structure them into a serpentine trace, place it right at the edge of that suspended membrane, so that when it deflects, it bends the silicon. And we can measure the resistance of that piezoresistive strain gauge and infer the degree of bending in that way. And the whole thing can be miniaturized, very tiny geometries. This is the tip of a pencil, and that's the entire device there. We've done the full finite element modeling, so we know exactly the mechanics of how that deflection occurs, and we know exactly what kind of resistance changes correspond to those different deflections. So if you build one of these pressure sensors, you can compare its response to a commercial sensor over a range of intracranial pressures that's clinically relevant, between 0 and 80 millimeters of mercury. So this is the commercial sensor. The transient sensor, we measure out a resistance, and then we calibrate that resistance to pressure. It's just a linear calibration constant that relates those two quantities. So if you do that calibration, you can develop a pressure reading out of this bioresorbable sensor that's in quantitative agreement with the commercial sensors. You can see here, due to its response to this pressure transient. So this is time we're just varying the pressure and comparing the response of the commercial to the transient device. So that's in vitro operation in deionized water. You can do in vitro operation in artificial cerebrospinal fluid at physiological temperatures, 37 degrees. And you can look into the response of both the commercial and transient sensor to different pressure waveforms as a function of time. So we can run it out to 4 or 5 days or so without losing any accuracy. And 5 days is on the front edge of the kind of operational window that you'd like to have available in a clinical setting. So we'd like to push that out a little bit, but we're already in a range that has practical utility. So you can take that kind of device and you can do animal tests with it, and I'll show you some results now of what that looks like. So at Washington University, you have rat models for traumatic brain injury. So we insert into the intracranial space these resorbable pressure and temperature sensors. Turns out temperature is really easy. I won't even describe how you do that, but you can do that, both of them. And then you can use very fine molybdenum wires that come up through the suture site. So these wires are actually smaller in diameter than the suture thread themselves, and so they don't prevent suturing of the wound. And then you connect those wires to a head-mounted stage that does wireless data transfer. So you can make measurements of intracranial pressure and temperature in vivo then in this way. And let me show you a couple of examples of that. So this is commercial and transient sensor measuring temperature. So commercial sensor temperature is over here. We're using temperature-dependent resistance in silicon trace to do the transient sensing, illustrated in red here. And this corresponds to the time immediately after the surgery. The rat is coming out of anesthesia, and as a result, it begins to warm up. And so the intracranial temperature increases gradually. And then our collaborators take the rat and immerse it in what they call an ice sauna, basically cools the whole rat down and causes another time-dependent variation in the temperature. And the commercial and the transient sensors are tracking very nicely. Temperature is easy, pressure is much harder. Here's an example of resistance measured out of one of these transient sensors as a function of time. And what you see here is basically more or less a constant baseline as what you would expect. But then on top of that are some oscillations. This is just associated with respiration. So as the rat breathes in and out, the intracranial pressure actually changes in a periodic way. And then what you see here are these spikes intermittently. This is called this Terechik response. It basically corresponds to squeezing of the abdomen. So our collaborators take the rat and squeeze the abdomen, and actually creates pressure transients in the intracranial space. And that's what you're seeing here. Squeeze, 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 squeeze. And the peak in the pressure that you measure with these transient sensors is very well aligned with the pressure response you measure in one of these commercial sensors. The key, though, is you don't have to extract these devices. They can remain in the intracranial space and will completely dissolve in a few months. So that's one example. Another is actually simpler. You can actually use silicon electrodes to measure surface electrical activity on the brain. So you can do electrocorticography with transient electronics. And in this case, you can achieve chronic operation, functional operation up to 30 days of implantation. So these are 3 channels of transient electrode array compared to a control, which corresponds to a stainless steel pin. You see very good agreement between these 2 methods for measurement. But the key uniqueness in these transient devices is their ability to bioresorb over time. That's a passive electrode array. You can actually do active matrix addressing because you have access to high quality transistors. So you can do not only small numbers of channels, but dense arrays as well. So this is an example of a transient electrocorticography system built around silicon nanomembrane electronics. Okay, so for the last 10-15 minutes, let me talk to you about something that's totally different, but related and something of interest to us, so hopefully you find some interest as well. So if you think about the devices I've described to you thus far, they have this soft mechanics that allows their integration on biological surfaces. Heart, brain, skin, that type of thing. That offers a lot of functionality, but you have to be mindful that biology is fully three-dimensional. So you can do useful things on surfaces, but you're missing out on a lot of the important function of the organ. So the brain obviously is a three-dimensional network. Neural circuits that have activity that can be measured from the surface, but also functionality that penetrates down into the depth of the system. That's nothing new. We just want to highlight that. It's not just neural circuits though, but vasculature. Everything in biology is three-dimensional. So if you look at the vasculature in the heart, it's like in some ways the geometry of the neural circuits in the brain, in the sense that it's open, three-dimensional network type architectures. And so if you're thinking about biointegration, how to bring material science and advanced electronic function to biology, it would be nice to be able to construct electronic circuits with this kind of open network layout. And so the question is, how could you go about doing that? Preferably with this as the starting point, because this is so spectacularly well developed.
if you want to do anything in electronics, it would be wise to have those activities well aligned with this type of platform. So the question becomes, how do I take silicon CMOS in this type of planar geometry and try to configure the system so that the active components of those circuits can move up out of the plane and form these more three-dimensional architectures reminiscent of those found in biology. How can you do that? And that's a question we've been thinking about for a number of years, and weren't clear on whether there was a solution at all. But I think over the last couple of years, we're beginning to believe that, in fact, there is a way to do that. And that's what I'll tell you about in the next 15 minutes. So here's the strategy that allows you access to that kind of 3D architecture, starting with a 2D piece of electronics on silicon. It relies on a couple of things I've already told you. It relies on the ability to slice the active silicon and the devices off of the near surface region of the wafer. I showed you how to do that already. I'm not going to go back through that. So let's say you do that. And in this case, we create, as a simple example, a piece of silicon nanomembrane electronics that's in this geometry of a serpentine filament, whose amplitude decreases continuously as a function of position along its length. So create this kind of green structure using those kind of undercut etching lithographic processes I described before. Take it off the silicon wafer. Meanwhile, use a piece of silicon that offers very high elongation as a substrate. So this is a piece of silicon you could stretch 300–400% with linear elastic mechanics. You stretch it out. So it starts like this. You stretch it out uniaxially in this way. And then you functionalize the surface of the silicon so that you have hydroxyl groups exposed. It turns out that you can do the same thing on the back side of the silicon, and you can do that lithographically. So you can create corresponding hydroxyl groups at lithographically defined locations, which I'm identifying here with these red dots. If you do those two things and you bring those two pieces of material together, then upon contact you will get covalent bonds that will form at those red dots due to dehydration reactions of the exposed hydroxyl groups. Everywhere else you just have van der Waals interactions, so very weak adhesion. The consequence of that is when you relax this pre-stretch, you allow the substrate to go back to its original dimensions, the compressive stresses that begin to act on this filament will cause the unbonded regions to delaminate, move up out of the plane, rotate, translate, and twist as defined by the geometry of this 2D precursor and the configuration of bonding sites, such in this particular case, the net consequence of that process is it transforms this 2D filament into this 3D conical helix. And I'll show you how that happens in this movie. So this is a few different views associated with the process. And this movie will show you what happens when you begin to relax that pre-strain. So it goes from 2D to 3D. In this case, very simple geometry. I showed you much more complex cases in a little bit, with the bonding sites defining the overall geometries, the front view, side view, top view, and 3D view. So this is what it looks like, full modeling of that process into the released silicone. You have residual stresses only at the bonding locations. Everything else is completely relaxed back to the original dimensions. You can compute the stresses and strains associated with that bending and that twisting process. And so with finite element modeling as a tool, you can design systems that avoid any kind of fraction-reducing strains in the silicon. In this case, here's the experimental image. It's colorized SEM. You can spool up that very thin silicon into these kind of 3D conical geometries. You can do simple helices, and you can control the handedness, the chirality of those helices. This is a dashed line separating an array of right-handed coils from left-handed coils. Just change the geometry and change the positions of the bonding sites. You can control that. You can cause it to switch midstream, so right, and then abruptly shift to left. So that would be a case of anti-Helmholtz coils, again in device-grade monocrystalline silicon, compatible with full integrated circuits as well. You can do this with biaxial strain, not just uniaxial, so you can begin to create more three-dimensional structures. These are toroids that will form as a result of these closed-loop filamentary serpentines here and here, and then sort of a basket structure in the middle as a result of that type of assembly process. There it goes. So now we're relaxing biaxial strain. We're straining the substrate in both directions. As we relax that, it causes that kind of geometrical transformation. And of course, you can do that with real silicon. This is a SEM view, sort of top view, angled view, FEM of similar views. We quantitative correspondence between modeling and experiment in that way. And so this kind of finite element approach allows, very powerful design tool. So those are coils. Coils are interesting, but you can imagine lots of different things. You could build all kinds of building blocks this way, sort of tables and tents and starfish, rotated tables, boxes, 3-layer flowers, baskets, all kinds of structures, where the 3D geometry is defined by the pre-strain on the substrate, the 2D precursor layout, and the bonding site configurations. So you can imagine all kinds of different geometries, and you can build those in isolation, or you can build interconnected arrays of them. In all of these cases, we sort of have one level of buckling, buckles up to a given height, but you can do more than that. You can create hierarchical structures, where you have buckled structures that form on top of buckled structures. There's one buckling level, there's another one, 1, 2, here's 3, 1, 2, 3, all the way up here. In this case, the z-axis height is actually larger than either the x-axis or y-axis distance that's defining the base platform. You can do coils on top of coils. Here's an orthogonal array of coils running in this direction and this direction, where that latter array of coils is sitting on top of the first array of coils. And so here's an example of that. This is the 2D precursor. You play the movie. This is biaxial strain. You relax it. Moves up out of the plane to form what begins to look like kind of an open network mesh geometry that we had in mind for this sort of biological inspired layout. Here's an example of a structure of that type. You can build these things defect-free. You can see the coils running in this direction, running in this direction. The three-dimensionality is really highlighted by cross-sectional views. And you can see these loopy things spiraling up like this. In this case, the silicon is about a half micron thick, about 20 microns in width. But the idea is scale to very small dimensions as well. And here's an example of 100 nanometer thick ribbons of silicon, about 700 nanometers wide, in this kind of starfish shape with overlaid FEM results on top of that. So you can do this not only in arrays and coils. You can make all kinds of really funky things. This is an example of something my students put together. I have no idea what this is. It's like tilted tables and flat tables and then baskets and things like this. It looks like some kind of painting by Salvador Dali is what it reminds me of anyway. But you can begin to do things not only in filaments but also in sheets. And so you can think about this as sort of a self-assembling sort of kirigami type of approach, where in this case we have a membrane, and then the cuts define a lot of the geometrical properties in this case. And so this particular sheet gets crinkled and folded up in a funny type of tint geometry as a result of the bonding sites, and now the positions of the cuts provide an additional degree of freedom in defining the layout. So here's an example. This is the FEM modeling. There's a piece of silicon sort of folded up into a funny shape, kind of in that way. And then you can do lots and lots of different geometries, look at hundreds of these things, and there's a lot of versatility in the layouts. And now you can begin to combine filaments with membranes. This is the last example that I'll show you. So in this case, the 2D precursor has this type of layout, a big plate here, some very small kirigami cuts here, and then this kind of toroidal filamentary serpentine around the outside. And this gets into a geometry where it's not necessarily intuitive in terms of what 3D structure will result from assembly, starting with that 2D precursor. But in this particular case, you form this kind of funny sunflower or like umbrella structure as a result of that assembly process. And you can kind of see that as well in silicon. So this is the finite element modeling. This is the silicon structure. Again, I have no idea what that's useful for, but it is kind of a funky layout. And it just begins to give you a flavor of the geometric versatility you have with these kinds of ideas. So back to biology. That was our main motivation. So if you think about these 3D things, it probably does not make sense to try to smush them into the brain, for example, as a biointerface. But nevertheless, they can be interesting as active electronic scaffolds. So build the 3D structure and then grow cells on top of it. And so it turns out you can functionalize the surface of the silicon to make it biocompatible and adherent for cells. And you can deliver cells, for example, on top of this platform and allow them to proliferate and propagate down these down these supporting struts. They sort of align to those kinds of geometries, and at the same time you have active electronics integrated, so you can imagine monitoring their proliferation, maybe even stimulating them to yield targeted outcomes. So this is very much exploratory, but this is the way that we're thinking of biointegration in terms of active electronic cell scaffolds, so silicon jungle gyms for cells, essentially. So with that, let me just conclude and wrap up then. A lot of this work is highly interdisciplinary, so we have lots of senior collaborators. Younggang Huang is the theoretical mechanician at Northwestern. He does all the mechanics computations I was referring to. Placid Ferreira, sort of the manufacturing guy in mechanical engineering at Illinois. A lot of these systems require unusual manufacturing approaches. I didn't talk a lot about that, but he's a key person. Shuling Li on MOCD, Ralph Muzo on surface chemistry. And then we work very closely with practicing clinicians, in this case for the electrophotography in the context of epilepsy, and for those intracranial pressure sensors, traumatic brain injury, Rory Murphy, the expert at Washington University. So those people are important, but the students and the postdocs are the most important because they do all the work. And I just get to talk about it. I've been very fortunate to have been able to advise many talented grad students and postdocs over the years. This is a picture from a group party. This actually makes the group look bigger than it really is because that is not a postdoc and that's not a graduate student. But I want to thank them. Thank you for your attention. Grazie.
Very much for the great presentation. We have now some minutes for maybe a couple of questions from the audience, if any. Okay, I will have one just to break the ice. About the three-dimensional self-assembling of the circuits out of the plate, can you give us some numbers about how much is reversible the process? I mean, can you stretch again and do it two-dimensional again, and how many times?
Yeah, so that's a great question. All of this is just linear elastic mechanics, so it's fully reversible. The silicon strains are always engineered up front to be less than maybe 0.5%. Silicon starts to fracture. It's a very abrupt fracture threshold, right around 1%. So if the silicon doesn't break, you're more or less still in the linear elastic regime. And so the consequence of that is you can stretch the substrate back out and the structure will go back into its flat initial 2D precursor geometry. The other consequence is that if I try to, let's say, release this thing, so if I undercut etch these pads, this thing will not float away as this in the geometry that you're seeing here, in this sort of sunflower geometry. It will snap back to this planar layout. So one interesting question then is how do you lock these structures into this kind of geometry? And that's something that we've been thinking about and working on the last few months. But to your point of reversibility, you know, again, if you release it from the substrate back to 2D, if you stretch it out in the same kind of biaxial configuration you started, it will be back in the 3D geometry. You don't necessarily have to stretch it that way, though. For example, you could do it uniaxially along this direction or uniaxially along this direction, in which case you will tune it into another kind of 3D form. It's not planar, but will be, you know, in a different configuration. So it's tunable mechanically.
And you don't have issues related to the stability of the covalent islands to take it on the substrate, I mean.
So the adhesion here,
yeah.
So this is a very challenging part of the surface chemistry. So I mentioned these kind of hydroxylated surfaces, and when you bring them together, you evolve water, and you end up with an oxygen-silicon-oxygen bond at the interface. But these pads have to support significant stresses to hold this thing in that kind of geometry. So getting the surface chemistry right here is critically important in making this type of approach work.
Thank you. Other questions? Please. Just speak loud because we don't have...
One is about, you showed some AFM images of the silicon membrane, and you showed also that basically as soon as the thickness is very, as soon as the material is very thin, then basically the silicon becomes bumpy. So did you have problems to measure the same membrane with the AFM? Did you have to change the frequency, for example?
So let me go back to the image that I think you're referring to. It's way back at the beginning of the talk. That was actually an SEM, so it was an angle view SEM. This one?
No.
No.
This one.
Yeah. So the way that we're measuring these, so every data point here corresponds to the silicon wafer. So it's a silicon wafer, it's SOI wafers, silicon wafers supporting those membranes. So they're not floating around by any means. You can grab the chip, immerse it in the fluid, hold it there, let's say for a day. Then we pull it out, dry it off, do the AFN, then reimmerse. And so you could wonder, when you pull it out, is it forming a native oxide? Then you measure, then you put it back in, you dissolve the native oxide, you pull it out, you form another one. So you're not really dissolving silicon, you're just dissolving native oxide and working your way through like that. We're worried about that, but the easy way to study that is to just change the time interval. So you can pull it out every day, every 3 days, every 5 days. It doesn't change the kinetics. So that's the way we're measuring. We're not trying to do the AFM in situ under the water. We just pull it out and measure it, and that was the control experiment that we did to make sure that the native oxide was not really having a significant effect on the kinetics that we're measuring.
Okay, thank you.
Yeah.
Other question over there?
Thank you for your talk. I am interested in the TBI application. Is the sensor that you are putting in the brain are compatible with standard diagnostic techniques like magnetic resonance imaging?
That's a great question, and we have not done that test. We do need to do it, and we appreciate that you can't put a device in that would prevent MRI, because you have to be able to do that. So we feel that there's not a problem, there won't be a problem, because we don't have a lot of conductive material. I mean, I think that would be the concern, is that the RF pulses used in doing the MRI imaging would induce heating in the chip, and then that would have an adverse consequence on the brain, So we don't think that it's a problem, but we have not done the test. We need to do it. It's a very, very good question. And I think we'll do that at an animal level first. But most of the material is non-conductive. We have some metallization here for the pads that are needed to do the piezo-resistive readout. And then we have these very fine molybdenum wires as the interconnects coming out through the suture. So it's not as though we can completely ignore the potential risk of doing MRI imaging, but I think it's unlikely to be a problem, but we need to do that.
Maybe one last question. No last question? So, okay, so in the interest of time, I would like to thank Professor Rogers again. We proceed for the second plenary presentation of the conference.